Welcome to Work on It Wednesdays. Today we are going to finish up question 2 of this grade 11 paper, which has basically question 2.7 and 2.8. 2.8 consists of 2.8.1 and 2.8.2, but it's not that long. Okay, so 2.7, refer to the figure. A rectangle has side lengths of root 5 plus 1. I drew the rectangle here. There's side lengths of root 5 plus 1 and root 5 minus 1. Then they give the sketch there and they say calculate the length of the diagonal. Now hopefully you know the diagonal is this line going across from corner to corner. Let me just try and draw it neatly there. Or this line. But since I've got these two sides, I'm going to work that diagonal, not that one. And leave your answer in simplest third form. So I'm going to calculate the length of the diagonal. Now, you must first just know that a rectangle has a 90-degree angle. And then I can just use the Theorem of Pythagoras for that. I'm just going to call this let's call the diagonal D. If you call things, if you name things to use them in your calculations, you must have the sketch here so that you can draw the line that you're naming on the sketch. So that if I now use a D here, if I have the sketch in my answer book, then the people can see, the person who marks my work can see where I got that. But if you write the D in your question paper, they don't always have your question paper with you, with them as they mark. So please, if you put in values in a sketch, you must just copy the sketch in your answer book. Okay, so this is the Theorem of Pythagoras, is that D squared equals that squared plus that squared. And then I can work this out. So I can't just say root 5 squared plus 1 squared. Be careful, please. That's a very proper catching point that a lot of students make. I must write the brackets, both of them, twice, so that I go and find the product. Nope, that's a minus. Okay, and then I'm going to multiply root 5 times root 5 is just 5. Root 5 times 1 is root 5. Root 5 times 1 is root 5, and 1 times 1 is 1. And then root 5 times root 5 is 5, minus root 5, minus root 5, plus 1. Okay, and now I can count all of the like terms together. Now numbers, I just count like I usually do. If you didn't know this, roots you can add like terms. So if this was x plus x, it would be 2x. So root 5 plus root 5 is 2 root 5. And then minus root 5 minus root 5 is minus 2 root 5. So they actually cancel one another out there. And then I have 5 plus 1 is 6 plus 5 is 11 plus 1 is 12. Okay. And they did not give me units that I'm working in. So if you don't have units, then you write units. Okay, now this is D squared. So I must now just work out D will then be root of 12. And to write 12 in its simplest third form, I'm going to find its prime factors. Divided by 2 is 3. So I'm going to find its prime factors and substitute in the place of 12 the prime factor form, because then I can work out the root of 2 squared is 2. And then the root of 3 I can't work out, so I'm going to leave it like that. Right, so that is question 2.7. Let's look at 2.8. Okay, in 2.8 they say, in January 1999, by working out 2 to the power of 302,1377 minus 1, A computer took 46 hours to find the largest prime number. It contained 909,526 digits. So if I multiply this, it's a number that has, this is 1 digit, this is 2 digits, this is 3 digits, okay? So it has this amount of digits. It's a huge number. Then they say, suppose you were to write out this number, not this number, the number with 909,526 digits. You were to write out this number at 1 digit per second, with each set of 10 digits taking up to 5 centimeters of space. Then question 2.8.1 says, calculate the time it would take for you to write out the number, showing that this would be more than a week. Okay, so if I write out 1 digit per second, I'm going to work on 909,526 seconds basically, because this is the amount of digits I have, and if I write one of them per second, I'm going to write for 909,526 seconds. 909,526, and then if I divide this by 60, I'm going to go to minutes. So divide this by 60, that is 15,158,76667 minutes. And if I go to hours, I'm going to divide it by 60 again. Then I have 252,6461 recurring, so 11111 hours. Let's just write 11111 hours. And then if I'm going to go to days from there, I'm going to divide with 24 hours in a day. This is the amount of hours. If I divide that by 24, then I have 10,5269 days, which is more than a week. More than a week. Okay, 10 days, it's a week and 3 days, and the 4th day, it's going to be some more, like half of the 4th day also in the next week. And that is if you don't sleep or eat or anything. If you just sit and write continuously, it's going to take you more than a week to just write down this number 1 digit per second. Right, so that's just to give you an idea of how long this prime number is. It's one of the biggest. In last year, they found a new prime number, which is even bigger than this. But this is a big prime number that they found in 1999. Okay. So then in 2.8.2, it says find the length of the number when written out in kilometers. So the number is 909,526 digits long, and they say for every 10 digits, it takes up 5 centimeters of space. So this is the amount of digits I have. I'm going to divide that by 10, 909,526 divided by 10, and then it gives me 909,522, which I can actually calculate without a calculator, 0.6, 5 centimeters. This is the amount of 5 centimeter spaces I have. And then this I'm going to multiply with 5 centimeters. So that I get the amount in the distance in centimeters. So I'm going to multiply that by 5. Then I have 454,763 centimeters. Okay. And then now I want to convert this, because they say I must give my answer in kilometers. Now to go from centimeters to meters, I'm going to divide by 1,000. And to go from meters to kilometers, I'm going to divide by 100 from centimeters. Sorry. To go from centimeters to meters, I must divide by 100. Okay, which is the decimal point is then there. And then to go from meters to kilometers, I must go back 3 spaces more, which means I'm going to have 4.54763 kilometers, or if I round this off to 2 decimals, 4.55 kilometers. That's if I write 10 digits in a 5 centimeter space. Let me just get a centimeter here quickly. That's basically a centimeter. No, so 3, 2, 3, 4, 5. That's if I write 10 digits in this bigger space, basically. So I write 10 numbers there, which is, if you see here, I wrote 1, 2, 3, 4, 5, 6 numbers in about that space. So if I write 10 digits in this space, so I must write smaller than this, then the number is going to be 4.55 kilometers long. It's ridiculous. Right, so that's an awesome question. I love it. And that's it for today. Hope to see you next week for Work on It Wednesdays.